I'm now going to talk through AS Chemistry Paper 2, Specimen version 0.5. So I'm going to look first of all at question number 1. Question number 1, 1.1. Compound J, known as leaf alcohol, has the structural formula CH3CH2 CH2CH2OH. Produced in small quantities by many green plants, the E isomer of J is responsible for the smell of freshly cut grass. Give the structure of the E isomer of J. Well, I'm actually going to do spoilers to start off with because you can see what it looks like. So the E isomer of J, if we actually look here, it's got a double bond between the two carbons. A structural isomer like this, an EZ isomer, sometimes called a geometric isomer, is part of a larger family of isomers called stereoisomers. So a geometric isomer is a stereoisomer, and it happens because of this double bond. So if you're asked why it happens, this double bond has no free rotation. Essentially it can't spin, and so it locks the positions of the other groups of atoms around it into space. But we say it has no free rotation. If you're asked for the definition of an EZ isomer, or a stereoisomer, or a geometric isomer, so EZ isomers or geometric isomers, part of a larger family of stereoisomers, the definition, not why it happens, but the definition is that they have the same structural formula, but a different arrangement of atoms in space. The different arrangement of atoms in space is a consequence of that double bond having no free rotation. So let's have a look at why we're saying this is the E isomer. What do? We look to the left of the double bond and we look to this carbon and we trace along to see what it's bonded to. It's bonded down here, it's bonded to an H. Up here it's actually bonded to that C. So you have a look at the two atoms that it's bonded to the left. This one is bonded to an H with a lower atomic mass, an atomic mass of 1. This carbon has an atomic mass of 12. So we put a ring around this and highlight it. We say this group here takes priority because that carbon joined to the C, as opposed to this H joined to the C, that carbon has a higher atomic mass. And then we look to the right hand side of the double bond and we look at this carbon here. This carbon here has an H bonded to it and a C bonded to it. So of the two atoms there bonded to this C here has got a higher atomic mass than the H. And so this group gets highlighted. This group has priority. So this group here and this group here have priority. They're opposite each other across the double bond, and so it's the E isomer. If this group were on the top, or the two groups taking priority were on the top or on the bottom, they're on the same side, and it would be a Z isomer. Just incidentally, one thing I didn't say is how do I check if this has geometric or stereoisomers at all? Well, I look to the left of the double bond on the carbon here. If this group and this group are different, and to the right of the double bond this group and this group are different, it will have geometric isomers. It only doesn't have geometric isomers if these two are the same or these two are the same. Draw the skeletal formula of the organic product when J is dehydrated using concentrated sulfuric acid. Well, you've got to know what the word dehydrated means. Concentrated sulfuric acid removes water. The way that it removes water is, if you look at these two carbons here, on one side of the carbon it removes an H from there, and on the other side, the other carbon, it removes an OH. So it happens when two carbons have an OH on one side and an H on the other side of the two carbons. And when that H is removed and that OH is removed, it makes water. And between the two carbons you get a double bond. So let's actually have a look what's going to happen. We're going to have CH3, CH2 with a single bond between the two, a single bond then down to the C, a double bond between these two C's, a single bond down to this C, and after that H and that OH have been removed by the concentrated sulfuric acid and remove water, you'll end up with a double bond here. You'll have CH there and CH2 remaining there. So we're going to have single, single, double, single, double. 1, 2, 3, 4, 5, 6 carbons in a line, and it will look like that. So the way that we do a skeletal formula is we count the number of carbons, 1, 2, 3, 4, 5, 6. We put them in a zigzag shape, 1, 2, 3, 4, 5, 6. There's a carbon at every point on this line. We remove the H's, we never draw the H's, and the double bonds are single, single. There's the 2 singles. Then we hit a double bond. Then there's a single bond, that's that one there, and we've made a double bond between these 2 carbons. There it is, because we've removed an H and an OH in making water when it's been dehydrated by concentrated sulfuric acid. Let's have a look at the next one here. So this one here, if I were to look at this, if I went to the left of the double bond, I've got a carbon joined to that carbon, and I've got a carbon joined to this carbon. That's an issue because both of those carbons have got the same atomic mass. So what do? I carry on further and have a look what these 2 carbons are joined to. Well, this carbon is joined to another carbon. This carbon is just joined to H's. So those 2 have got the same atom joined to this carbon, a carbon and a carbon, but when I go further along the bond, this carbon is joined to H's with a lower atomic mass than this carbon joined to a C, which has got a higher atomic mass. So we put a ring around this one because that carbon is joined to a carbon, this carbon is just joined to an H. This group here, called an ethyl group, this is a methyl group, 1 carbon, CH3, 2 carbons in a branch is an ethyl group. We put a ring around this ethyl group here, we say this takes priority. So the ethyl group takes priority over the methyl group. So now, consider the groups joined to the right hand side or the left hand side. We've done the left hand side first. Consider groups joined to the left hand side of the carbon-carbon bond. Both groups contain carbon atoms, so go 1 bond further, and the carbon, this carbon here, is joined to another carbon, so this group takes priority, the ethyl group takes priority over the methyl group. To the right hand side we then look. This is actually easier because this carbon here to the right hand side is bonded to a carbon. This way it's bonded to a hydrogen. So this carbon having an atomic mass of 12 compared to the hydrogen only having an atomic mass of 1. This has a higher atomic mass than this, and so this CH2OH group takes priority. We put a ring around that, and then we have a look and see which 2 groups have taken priority, which 2 we've highlighted. We've highlighted these 2. These 2 groups have taken priority. They're on the same side. They're both on the top of the double bond. They could be on the bottom of the double bond. They're on the same side of the double bond, and therefore it's a Z isomer. How do I then name it? How do I go about naming something? Well, first of all, I look at the longest carbon chain. 1, 2, 3, 4, 5 carbons in a row. So meth, eth, prop, but, pent. It's pent. Pentane or pentene? Well, it's got a double bond, so it's pentene. Now then, let's have a look what else is joined to the pentene. I've got an OH called an ol. It's an alcohol, ends in ol. And I've got this group here off the main carbon chain. This is a methyl group. Which end should I start labelling from? Well, I've got to try and give the lowest numbers. I'm going to start labelling from this carbon here, this end, because then the ol group will be at carbon number 1, the ene will be at carbon number 2, and the methyl will be carbon number 3. So I can use a 1, 2 and a 3, a 1 to describe the ol, a 2 to describe the ene, where the ene is, and a 3 to describe where the methyl group is. So I'm going to label from the right hand side, because if I label from the left, the numbers would be higher. Let's have a look and do spoilers and what it's called. 3-methyl, pent 2-ene-1-ol. I'll just talk about the fact that it's not ene, it's en rather than ene in a minute. Let's just look, let's just check. 3-methyl, yes, because 1, 2, 3, the methyl group is at number 3. On carbon number 2 is the ene, pent, 5 carbons in a row, 2-ene-1-ol. The ol, the OH group, is at number 1. So why have I lost an E? Well, if I disregard the numbers for a minute, I would have E-N-E-O-L. I'd have 2 letters next to each other. You disregard the number when you're looking at letters next to each other. And if I have two vowels together, an E and an O, I drop the E. That's just a rule, so that it becomes EN rather than EEN, because I'd have an E next to an O, and you can't have two vowels together. So 3-methyl pent-2-ene 1-ol. You could actually name that OH as a hydroxy group as well. So you could actually call it 1-hydroxy 3-methyl pent-2-ene and keep the ene as a group. Either would be allowed. Right, let's look at question 1.4. The effect of gentle heat on malic acid is shown below. So this must be malic acid, and this must be what's made along with water. So it's a condensation reaction. A reaction that releases water is a condensation reaction, and we say that the malic acid has had water removed or it's been dehydrated. The student predicted that the yield of the reaction, so making this, would be greater than 80%. Okay, in an experiment, 10 grams of malic acid were heated and 6.53 grams of the product were obtained. So I know where I'm going straight away with this. Why would I be given grams? The only reason I'd be given grams is to use this formula I've given to work out MR, and moles is number of grams divided by MR. So let's work out the MR of this, use the number of grams, and work out the number of moles of this. Moles is always a useful value to have. So now, if I look at the malic acid here, I've got two O's bonded as OHs here. There's no carbon on that corner. There's a carbon there, a carbon there, a carbon there, and a carbon there. There's 4 carbons on those corners, but these are just OHs. There's no carbon on that OH. So I've got 2 OH groups. I've got 1, 2, 3, 4 carbons and 2 O's either side. Now, I've just got to check that every carbon, each of this carbon here, this one here, this one here, and this one here, have actually got 4 bonds, because every carbon needs 4 bonds. That's got 4 bonds, a double and a single and a single, a double, a single and a single, that's okay. But these 2 carbons have only actually got 3 bonds. So why have they only got 3 bonds? Well, there's an H on there that's not seen. So on the skeletal formula, you don't draw H's. So I know that there's an H there, and this one's got this carbon here has got 3 bonds, there's an H there. So if I count up the number of H's, I've actually got 1, 2, 3, 4, 2 hidden H's there. I've got 4 O's and I've got 1, 2, 3, 4 carbons. If I do the MR, 4 times 12 for the carbons, 4 times 16 for the O's, and 4 times 1 for the H's will come out at 116. To work out number of moles, well, moles is mass divided by MR, so the moles of malic acid is 10 divided by 116, which comes out as 8.62 times 10 to the minus 2. What does that tell me? Well, I've got a reaction here. I've got no number in front of this, so I've got a 1. I've got no number in front of this, I've got a 1. And I've got no number in front of this, I've got a 1. It tells me that 1 mole of this makes 1 mole of this and 1 mole of this. Or 10 moles of this would make 10 and 10. Or 100 would make 100 and 100. I've got equal numbers of moles of this making equal numbers of moles of this. So I know my number of moles of this product is 8.62 times 10 to the minus 2. If it works out perfectly. So in a perfect world, if I get 100% of this, I'm going to get the same number of moles that I have of this. I'm going to get 8.62 times 10 to the minus 2. It probably won't work out that way, because in an experiment you never make 100% of something, you lose something along the way. But let's use 8.62 times 10 to the minus 2 moles of this, if I make 100% of it, and let's use its MR to work out the mass of this that I could have made. So 8.62 times 10 to the minus 2 moles of this, let's work out its MR. Well, let's see how many carbons I've got. I've got 1 there, I've got 1 there, I've got 1 there, and I've got 1 there. I've got 4 carbons, 3 O's. This carbon's got 4 bonds, that's okay. This carbon's got 4 bonds, that's okay. This carbon has actually only got 3 bonds, and so has this one. You know what? There's 2 H's again on the top of there, unseen, to make the 4th bond. So I've got 3 16s, 3 O's. I've got 1, 2, 3, 4 carbons at 12, mass 12 each, and I've got 2 H's, mass 1. So what I've got is, I have got a mass, an MR of 98. Now, moles is mass divided by MR, So moles times mR will give me the mass. Number of moles of this, 8.62 times 10 to the minus 2 multiplied by 98, which is the mR, tells me that I should make 8.45 grams if I get 100% yield, if everything works out perfectly. It's no surprise that I've got 6.53 grams. I've lost some along the way. Well, how do I work out the yield? That's what I should have made. That's what I did make. I divide the smaller one by the larger one, so 6.53 divided by 8.45 will give me a fraction, and I multiply it by 100 to get the percentage. So my percentage yield is 100 times the smaller number, what I actually did get the mass of the organic product that I made, divided by the mass of what I should have made, and it works out as 77.294. Now, let's actually look. I have got three numbers there, three significant figures, and three significant figures here. I count the O, the zeros, if they're to the right of other figures. So I've got 1, 2, 3. I've got to count those two because they're to the right of the 1 in my significant figures. Three significant figures there, three significant figures there. I've actually got 1, 2, 3, 4, 5 significant figures there. It can't be more accurate than the initial values that I'm given. I need to turn that into three significant figures. I need to round it up. 77.294 rounds up to 77.3, three significant figures. That is actually less than 80%, so the student was wrong. Question 2.4. A 50-gram sample of water was used in this experiment. Explain how you can measure the mass of water without using a balance. Well, you've got to know that water has a density of 1 gram per centimetre cubed. In other words, 50 grams, 1 gram is 1 centimetre cubed, 50 grams must be 50 centimetre cubed. If you're measuring out 50 centimetre cubed, therefore, which equals 50 grams, you could use a measuring cylinder. Question number 2. Figure 1 shows apparatus used in an experiment to determine the enthalpy of combustion of leaf alcohol. So what's the heat change, how much heat is given out when leaf alcohol is combusted, burnt, reacted with oxygen. So what have I got? I've got a 50-gram sample of water, I've got leaf alcohol in a burner, I've got the mass of the spirit burner before and afterwards, and I've got the the temperature of the water before and afterwards. First of all, however, it's asking to write an equation for the complete combustion of leaf alcohol. So it's given me the formula again of the leaf alcohol. So what's it got? It's got 6 C's, it's got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 H's and an O. So I've got C6 H12O, or you could put C6H11OH at the end if you wanted to. I've got oxygen as well that I'm going to combust it in, and it says complete combustion, so it's going to make carbon dioxide, CO2 and water as well. Incomplete combustion would make carbon monoxide, CO, or if it said it made a black solid, it would make C, carbon. But this says complete combustion, so that means that I'm going to make CO2 and water. So first of all, I've got C6H11OH, or I could write it as C6H12O if I wanted to. Either is acceptable. I've got oxygen because that's what I'm combusting it in. Combustion is a reaction with oxygen. I've got CO2 and water because that's what happens when you get complete combustion. Rather than CO and water, or C and water if there's incomplete combustion. CO2 and water, I've put 6's in, that's easy enough. 6 C's there, the only place that the C's go are here, so I must have 6 C's here. I've got 12 H's, 6 times 2 is 12 for the H's, and the H's are appearing here. Let's add up the number of oxygens then, that's the final step. 6 times 2 is 12, 6 times 1 is 6, 12 add 6 is 18 O's. I need 18 O's here. Well, let's not forget this one, I've got 1 here, so I must have 17 O's here. So I want a number here that multiplied by 2 gives 17. So the answer is going to be 8.5. 8.5 oxygens. Let's just check again. 6 C's, 6 C's, 12 H's, 6 times 2 is 12 H's. 1 add 8.5 times 2 is 17, 18 O's there. 6 times 2 is 12, add 6 times 1 is 6. Yes, my oxygen's balanced as well. So what am I going to do with this question? Well, let's have a look at the next one. I've been given specific heat capacity here. The only reason I've been given specific heat capacity is to have delta H, sometimes known as Q as well. Delta H or Q, the heat change, equals minus MC delta T. Delta T, triangle T, is temperature change. So I've got my heat change equals minus MC triangle T, temperature change. M is the mass of the water that I'm heating up there. C is my specific heat capacity, 4.18, and my temperature change are these two taken away. I ignore the mass of the spirit burner and the alcohol that's being released. I don't use that. M is the mass of the water that's being heated up and changed. So ignore these figures for now. So what have I got? I've got delta H, heat change, or Q, is minus 50 multiplied by 4.18, which is the specific heat capacity, multiplied by the temperature change. So my first job is to get the temperature change. It's gone from 20.7 to 40.8. It's gone up by 20.1. So my temperature range is 20.1, and then Q, or delta H, heat change, is minus, there should be a minus in there actually, minus 50 multiplied by 4.18, that's the mass. 50 is the mass of the water that I'm heating up there, minus 50 multiplied by 4.18, multiply, which is specific heat capacity, multiplied by triangle T, delta T, temperature change 20.1, 4201, and it's measured in joules because specific heat capacity is in joules per Kelvin per gram. It's got a J there, so that's in joules. You convert it to kilojoules if you want. Does it say it's got to be in kilojoules? No, it doesn't, as long as you've got the unit, so you can leave it in joules if you want, or you can convert to kilojoules. I'll show you that in a minute. 4201 joules is what it's measured in. And that's fine. That should be a minus actually, because it's a minus MC delta T. It's exothermic anyway, so that would mean it would be a minus. Let's have a look what's next then. So my next thing to do is to have a look at the mass of alcohol that's burnt, because that value should be per mole of alcohol that's burnt. Well, let's subtract those two. 56.38 minus 54.84 will give me the mass of alcohol burnt, and that's 0.54 grams. I've got the MR of the alcohol. I can work out the MR of the leaf alcohol. It doesn't tell me in the question, but that's my leaf alcohol, C6H11OH. So I've got 6 times 12 for the carbons, 11 times 1 for the hydrogens, 16, then there's times 1, there's 1 of those, and 1 for the H, and that will give me an MR of 100. So I know how much alcohol is burnt, 0.54 grams, by subtraction from those two. I know the MR of the alcohol. Why would I be given mass and MR to work out the number of moles? Moles of alcohol is 0.54 grams divided by the MR 100. I've got 0.0054 moles. So let's just have a look what we've got. We've got 0.0054 moles of alcohol releases 4,201 joules of energy. I need to know how many joules of energy would be released if I had 1 mole, not this small amount here, but 1 mole. So if that small amount, 0.0054, releases 4,201 joules, 1 mole, a larger amount, would release more energy. How do I scale up? Well, I take that number and I do 1 divided by that. So 1 divided by 0.054 is going to give me a number to scale up by. 1 divided by 0.054 multiplied by 4201 will give me the number, the amount of heat change, if I had 1 mole. Let's just check my calculation again. That's a small amount giving a small amount of joules. 1 mole would give a larger number of joules. 1 divided by 0.0054 is my my number to scale up by, multiplied by 4,201 gives a much larger number of joules. Yes, that's correct for a larger number of moles, 1 mole of alcohol. 778,000 joules per mole to the -1 means for 1 mole, and that's your answer there. If you wanted to divide by 1,000 and work it out as kilojoules per mole, you could do, but it doesn't tell you to do so. In this case, it's allowing either. State how your answer is likely to differ from the value quoted in reference sources. Well, look at this experiment. We're measuring the temperature of this. We're going to assume that the heat from this alcohol actually heats up all of that water in the beaker. It might not. I might get heat loss. So that's one answer. I might actually not fully combust some of the alcohol. Some of it might evaporate. I might not get full combustion, a full reaction of the alcohol. Some of it might evaporate. And I'll actually heat up the beaker as well. So the beaker will get hot and the water may not. So all of those are possible answers, although your main answer is going to be heat loss. Heat loss is going to be your main reason, although other answers are possible as well: incomplete combustion or heat transfer to the beaker and not the water. Oh, and let's have a look how it's going to differ. There's a mark for saying that it's less negative. How does that work out? Less negative, a smaller negative number. That's because not all of the heat will be measured. Some of it will be lost, and so it won't measure as much as large a temperature rise rather, so that number will be smaller. 20.1 will be smaller. You won't see the full temperature rise because some of the heat will be lost, and so you'll get a smaller temperature rise in there. 20.1 will be a smaller number, and so this will be a smaller number. It will be less negative. It might be something like -600,000 joules instead. Question 3. 2-bromo-2-methyl-pentane is heated with potassium hydroxide dissolved in ethanol. 2 structural isomers are formed. We'll look at this in a minute, but the first part of the question says, state the meaning of the term structural isomers. So a structural isomer is where you have the same molecular formula but a different structural formula. So a substance with the same molecular formula but a different structural formula. Instead of the word structural, you could replace structural with the word displayed or skeletal, but it's most common to say it's a compound or a substance with the same molecular formula but different structural formula. So what would be an example of that? Well, there's 3 kinds of structural isomers. There's something called a chain isomer, there's something called a position isomer, and there's something called a functional group isomer. So the first kind, the chain isomer, is where you shorten the chain and introduce a branch. So say, for example, if you had C4H10, you can draw that in 2 different ways. You could either have C4H10 as butane, or you could shorten the chain and introduce a branch and have it as 2-methylpropane, a chain isomer. Or the second kind is that you can change the position of a functional group. A functional group is what identifies the compound, something in there that you see that identifies it. So say, for example, propane 1-ol, you could change to propan 2-ol. So you're keeping it as a propane, 3 in a line. You're not shortening the branch and introducing a chain. That would be chain isomer. This is position isomer, where you're changing the position of the OH, the functional group, from propan 1-ol to propan 2-ol. The key is the number changes the position of the ol, the OH group, the alcohol group. Or say, for example, you could change the functional group. So you could change something maybe from having say, for example, a ketone into an aldehyde, where you've got a C double bond O. You could change it from the middle of a chain into the end of a chain, so from a ketone to an alcohol. Another way of doing it would be, say, for example, if you had C4H8, you could do that as introduce a double bond, so it could be butene, say, for example, but then if you draw it as a cyclic compound, it can be cyclobutane, so ene to ane, and that's a functional group change. A functional group isomer. Now then, let's have a look at the mechanism for one of the isomers. So what's a clue in here? Well, heated, heat and ethanol, sometimes called ethanolic solution. So if there's heat or warmth and ethanol or ethanolic solution, it's something called an elimination reaction, where something is removed, eliminated. The other kind is if it's cold in water or aqueous, meaning water, cold aqueous solution or cold water, then you get something called nucleophilic substitution. But this one is warm ethanol. Let's have a look what happens. First of all, the potassium hydroxide, you never include the potassium part. The potassium part is something called a spectator ion. Similarly, if I had sodium hydroxide, you wouldn't include the sodium part. It's the hydroxide part that's involved in the mechanism. Let's do a quick spoiler. An OH minus, the minus can go anywhere really. I don't really mind where it goes. It actually does go on the O, but as long as you've got OH minus, the minus somewhere around here, and as long as you've got the lone pair on the O, then that will suffice. But you don't involve the potassium at all, and similarly sodium hydroxide, you wouldn't involve the sodium. OH minus with a lone pair of electrons on the O. Now you need to draw 2-bromo-2-methyl pentane. Let's have a look at that. 1, 2, 3, 4, 5. So it is pentane, 5 in a line. Longest chain is 5. All single bonds. So we've got the pentane bit right. 2-methyl. Well, if I start labelling from the left, 1 carbon, 2 carbons. There's the methyl group on carbon number 2. And on the same carbon, 2-bromo, I've got a Br on number 2. So carbon number 1, carbon 2. There's carbon 2, it's got a methyl group, and it's got a bromo group, a Br, a bromine atom. Okay, now the curly arrow comes from the lone pair on the O of the OH minus, and that attacks an H. Now, which H does it attack? Well, you go from the C, so you go from the Br down to the C, along another C, and it's an H from the C connected, bonded to the CBr. So let's go through that again. I've got a CBr there, the neighbouring C there as an H, and it's that H that it goes for. Now, this 2-bromo-2-methyl pentane doesn't know left from right, so I could go the other way and go to the right, from the Br down to the C and to a neighbouring C that way, and I could have that H as my one that it attacks. And that's why it says formation of one of the isomers, and 2 structural isomers are formed. It depends whether that OH minus and lone pair goes for that H on the C next to the CBr, or whether it goes for that H on the C next to the CBr. It could go for either of those two. In this mechanism that I've drawn, it's going from this H, and you need 3 arrows. So that OH minus is going to bond with that H. What will we make? HHO. And we'll lose the minus because the curly arrow is coming away from the O. We're going to make water from that. This bond needs to break to allow that H and OH minus to form the water, and those electrons go between the 2 C's, and we're going to end up with a double bond there, and the Br breaks off to allow that C to have a double bond here and 1 bond there and 1 bond there, and retain the number of bonds. You actually don't get a mark for drawing what's formed, but we're going to get water. We're going to get CH2, a double bond to a C, CH3, CH2, CH2, CH3. Incidentally, if it did go for the other way, then that arrow there would go onto that H, the bond would break and go into between those 2 carbons there, and the Br comes off. So in that case you get CH3, C, CH3, carbon to carbon double bond, that H would be lost, CH, CH2, CH3. 4.1. Glucose can decompose in the presence of microorganisms from a range of products. One of these is a carboxylic acid with a relative formula mass of 88, and it contains 40.9% carbon and 4.5% hydrogen by mass. If you add up 40.9 and 4.5, it doesn't come to 100%, and that's because a carboxylic acid has got oxygen in it as well. So the first step to do is to work out what percentage is left over, and that must be oxygen. So the percentage of oxygen is the 100%, take away the 40.9, take away 4.5, and so 54.6% is oxygen. Your next step to work out how many atoms of each there are as a ratio is to take each of the percentages and divide by the relative atomic masses of each of the atoms. So 40.9% divided by 12, which is the mass of a carbon atom, comes out as 3.41. 4.5 divided by 1, a hydrogen has an atomic mass of 1, is 4.5, and 54.6 divided by 16 is 3.41. So oxygen has got an atomic mass of 16. So that comes out as 3.41. Now, the problem is you've got to try and get these as whole numbers. So the easiest way to do that is to divide through by the smallest number. Divide all of them by 3.41. So if you divide all of them by 3.41, 3.41 becomes 1. That at least gets one whole number. 4.5 divided by 3.41 unfortunately comes out as 1.32. And 3.41 here becomes a 1. Now you've got to multiply up then to get this one to be a whole number. That's nearly 1 1/3, 1.33. So if I multiply by that by 3, it's going to become 4, more or less. That one by 3 becomes 3, so 3, 3, 3, 4 and 3. So if I multiply each of them by 3, I'm going to end up with 3 to 3.96, let's call it 4. It's an experiment after all. We can say 3 to 4 to 3. Okay, now then, if I had C3H4O3 and I add that up, so a carbon's 12, so 3 12s 36, add 4 1s, add 3 16s, it comes out as 88. And it says here that its MR is 88. So 343 is its molecular formula mass. So the molecular formula 88 is C3H4O3. The relative formula mass of 88 matches that. Therefore the molecular formula is the same as the simplest formula, 3 to 4 to 3. Write an equation for the reaction during fermentation. Well, you've got to know what glucose is for a start. You must know that glucose is C6H12O6. If you don't know that, you can't do that. You've got to know that during fermentation you make ethanol, and you've got to know that ethanol is C2H5OH, and you've also got to know that it makes carbon dioxide. If you don't know the formula of those three, and that glucose makes ethanol and carbon dioxide during fermentation, then you can't complete this question. The next part is that you've got to work out, you've got to balance it basically then. So what have I got in here? Well, the first thing I would look at is that the ethanol is the only product with H's in it. The CO2 doesn't have H's. So how many H's have I got in my ethanol? I've got 5 and 1 is 6, and I've got 12 H's. So that must be a 2. There's got to be a 2 in front of that, because 2 multiplied by 5 is 10, and 2 ones are 2 to make the 12. That's got to be a 2. So 2 carbons, 2 2s are 4 carbons. I need 6. That's got to be a 2 as well to balance the carbons. 2 times 2 is 4, times 2, add 2 times 1 is 2, 4 add 2 is 6. That will do it for me. Therefore, 06, 2 in front of that, 2 1s add a 2, 2 4s gets the oxygen as well. So there we go, that's going to balance that equation. Suggest one advantage and one disadvantage for industry of carrying out the fermentation at a higher temperature. So the fermentation is carried out at 35 degrees C rather than 25 degrees C in industry. Why would you do that? That's because you're going to increase the rate of the reaction. You're going to make the ethanol more quickly. So the ethanol is produced at a faster rate. One disadvantage is that you're going to need more energy. You're going to have to do it at a higher temperature, so it's going to use more energy. 4.4. The method used in 4.2 would result in the ethanol being contaminated by ethanoic acid. Why? Well, ethanol has got an OH bonded to a C, which is bonded to one other C. So the COH in ethanol, the C of the OH, the C bit of the OH, is bonded to one other carbon. We call that a primary alcohol. A primary alcohol like ethanol can be oxidized. So it can be oxidized and it will turn into ethanal, which is an aldehyde, and then it will further oxidize into something called ethanoic acid. Now there's a few ways that you can do that. You could add something like acidified potassium dichromate, which would go from orange to green and would do that. You'd have to heat it up, a process called reflux. But the other way that you could do it, it would also react with the air quite slowly, but it would oxidize in the presence of air, and the ethanol, a primary alcohol, would turn into an aldehyde, ethanal, and then into ethanoic acid. It looks as if the air's got in. Give two differences between the infrared spectrum of a carboxylic acid and that of an alcohol. Well, a carboxylic acid has got a C double bond OH on it, and an alcohol has just got an OH. But the spectra are different for a carboxylic acid's OH and an alcohol's OH. So an alcohol OH absorbs infrared light at a different place, a different frequency from the acid OH absorption. In other words, you get an absorption peak for an OH of an alcohol at a different place than you get an absorption peak for an OH on a carboxylic acid. And it's always worth referring to and writing the numbers down from your data book. The second one, of course, is that a carboxylic acid has got a C double bond O in it, and an alcohol hasn't got a C double bond O in it. So the C double bond O in acids has an absorption peak, and again, quote the numbers. Question number 5. CCl4 is an effective fire extinguisher and is no longer used because of its toxicity and its role in the depletion of the ozone layer. So depletion means to remove the ozone layer. Ozone is a form of oxygen. Instead of being O2, it's O3. In the upper atmosphere, a bond in the CCl4, well, that's carbon surrounded by 4 Cl atoms, bonded to 4 Cl atoms, so the bond that's broken must be a carbon to chlorine, breaks and the reactive species are formed. A reactive species that's formed in this case is called a radical. Identify the condition that causes a bond in CCl4, we know that's a C to Cl, to break in the upper atmosphere. Deduce an equation for the formation of the reactive species. Well, first of all, in the upper atmosphere, what happens is you get ultraviolet light from the sun, and that's the energy that's needed. The ultraviolet light provides the energy to break the bond. UV light. The equation, well, the CCl4, what actually happens is, in CCl4, one of the bonds between the C and the Cl breaks, and there's a pair of electrons in that bond that's forming a covalent bond. And actually, what happens is, between the C and the Cl, just one of the C to Cl's, the pair of electrons separate, and one electron goes onto the Cl as the bond breaks, and the other electron goes onto the C. Now that's come from the mark scheme. I've taken that from the mark scheme, but that dot, that unbonded electron, that's what it is, has come from a bond between the C and the Cl, a covalent bond, a shared pair of electrons, and that's actually gone back onto the C. We know it's gone back onto the C because the C has got 3 Cl's bonded to it, 3 chlorines bonded to it, and it should have 4 bonds. So that electron is on the C to make up for the fact that it's short of a bond. That unbonded electron on the Cl and on this radical as well makes both of these very reactive. One of the reactive species from CCl4 is this one, acts as a catalyst. It means it's going to be reformed in the decomposition, that's the breakdown of ozone. Write the 2 equations to show how the species acts as a catalyst. Well, first of all, we need this, Cl dot, that's the reactive species, and it's going to break down ozone. Now ozone's O3. Now there's only 2 forms of oxygen, O3 and O2, so it must make O2. The Cl dot, the chlorine radical here that's made the reactive species, reacts with O3, ozone, and the only thing it can make, The only other form of oxygen that there is O2. So O3 automatically forms O2. And then you can work out what's left. What haven't we used? Well, we haven't used a Cl, so that must be in there. There's O3, 3 O's makes 2 O's, O2. So there must be an O in there. And then there's a dot, which is an unbonded electron. We've got to show that as well. Now, what actually happens then is that it reacts again. So if it reacts again, then what's actually going to be formed? So well, ClO dot is going to react again. ClO dot with more ozone. So the depletion of the ozone layer is because the radicals keep reacting with ozone. So ClO dot will react with O3. The only thing it can make is O2, and we can have a look what's left over. So ClO dot that's made the radical reacts again with O3. Now, if it's making O2, look at this. O, O3, there's 4 O's on this side of the equation. 4 O's on this side of the equation, I can balance that up straight away by putting 2 in front of the O2. Now all the oxygens are accounted for and balanced. The only thing that's left then, I've not used a Cl, there it is, and I've not used a dot. And what I've actually done is I've made a catalyst, because the Cl dot rather, at the beginning of this equation has now reacted and reformed. So I've made a chlorine radical here. That unbonded electron makes it reactive, and so it's going to react again and deplete more and more and more ozone, and that's why there's a huge hole in the ozone layer. So any chemicals with Cl's in them, with a Cl in them, especially if the gases and can be released up into the upper atmosphere, are very, very dangerous because they form radicals. Next question. The next question is hard because of the units, so you've got to know how to convert units. So a small amount of Freon, CF3Cl, with a mass of 1.78 times 10 to the minus 4 kilograms, so kilograms first of all is a problem to us, escaped from a refrigerator into a room of volume 100 meters cubed. Meters cubed is a tricky unit to deal with as well. Assuming the Freon is evenly distributed throughout the room, calculate the number of Freon molecules in a volume of 500 centimeters cubed. So look here, we've got kilograms. We're used to working in grams. We've got meters cubed. We're used to working in decimeter cubed. And we've got centimeter cubed. So we've got a mismatch between some of the units. Give your answer the appropriate number of significant figures. So we've got to work that out as well. And then we've got Avogadro's constant, 6.02 times 10 to the power of 23. A very large number. That's the number of particles that are in a mole of substance. So we've got a lot of numbers with difficult units to deal with. So how do we start off? What can we start off with? Well, what have we got? We've got a named molecule with a formula, CF3Cl, and we've got a mass. It's in kilograms, but we can convert that to grams if we want to. So we can times that by 1,000 and it'll come out in grams. I've got a mass in grams. I've got an MR. I can work out the MR of this. A carbon has got a mass of 12. A fluorine has got a mass of 19. And Cl has got a mass of 35.5. I've got an MR. I've got a mass in grams. I can work out number of moles of this. Numbers of moles. Moles is a good unit to work with. So let's do that first of all. So the MR of CF3Cl, when you work it out, a 12, 3 19s and a 35.5 is 104.5. I've got the MR of this. Now the mass of this, 1.78 times 10 to the minus 4 kilograms. There's 1,000 grams in a kilogram. So to convert that kilograms into grams, I multiply by 1,000. So that's my next step. I multiply by 1,000. 1.78 times 10 to the minus 4 times 1,000, 10 to the power 3. That's the number of grams. So moles equals the number of grams divided by the MR. Moles is mass divided by MR. So I've put the mass into grams by taking the kilograms and multiplying by 1,000. That's now the mass in grams. Moles is mass in grams divided by the MR that I've worked out, and it comes out as 1.70 times 10 to the minus 3. I've got the moles. Now that's your first step. If you see something with a formula and you've got a mass, it will want you to work out moles. That's always going to be the first step. Now they're a little way in, then we can carry on. So, moles of Freon is that. I know that 1 mole of Freon, 1 mole of anything, the number of particles is that. I haven't got 1 mole of Freon, I've got 1.78 times 10 to the minus 3. But the number of moles that I have multiplied by Avogadro's number will tell me how many molecules or particles there are in there. So I've got that number of moles, I haven't got 1. 1 mole would be that amount, that number of molecules or particles. I've got that number of moles. So if I multiply that by Avogadro's constant, it gives me this number. This number, 1.02 times 10 to the power 21, is the number of particles or molecules that I have in that number of moles, that number of kilograms of Freon. That's the number of particles or molecules that I have of Freon. Now, that escapes into 100 meters cubed. I want to know if I've got that number of particles in 100 meters cubed. If I took a sample of it, 500 centimeters cubed, how many particles would I have? Well, I need to do another little bit of maths, and I'm just going to do this to the side. 100 meters cubed. Well, a meter is 100 centimeters. If I had a cubic meter, a cube that was a meter by a meter by a meter. To do a cube, I take the height multiplied by the length and multiplied by the width. Now a meter is 100 centimeters cubed. So I've got 100 centimeters cubed height cube, 100 centimeters width cube, and 100 centimeters length cube. 100 times 100 by 100 is 1, 2, 3, 4, 5, 6. That's the number of centimeters cubed. A million, 1 times 10 to the power 6, 1 with 6 noughts. That is the number of centimeters cubed in a meter cubed. And it says I've got 100 meter cubed. So that's number of centimeter cubed in a meter cubed. I've got 100 meter cubed. So that is the number of centimeters cubed. 1 with 8 zeros, 1 times 10 to the power of 8. That's the number of centimeter cubed in 100 meter cubed. I have now got that in centimeter cubed. 100 meter cubed is 1 times 10 to the power of 8, 1 with 8 zeros, centimeter cubed. I only need 500 centimeter cubed, so I'm going to do a fraction. 500 divided by 1 times 10 to the power of 8 is 5 times 10 to the minus 6. That is how much I've got to scale down by. I've got to multiply this number to bring 100 meters cubed down to 500 centimeter cubed, because I know how many particles are in 100 meter cubed. I need to scale down to work out how many particles are only in 500 centimeter cube sample. So that's the number I'm scaling down by. So the number of molecules in 500 centimeter cubed is this number of particles that I had multiplied by my scaling down factor, 5 times 10 to the minus 6, and it comes out as 5.10 times 10 to the power of 15. How do I know about significant figures? What do I do? Well, when I'm looking at numbers here, I've got 1.78 times 10 to the minus 4. I forget about the 10 to the minus 4 when I'm looking at significant figures. I just look at this number here. Forget about the times 10 to the minus 4. 1.78. I've got 3 significant figures there, a 1, a 7 and an 8. 3 significant figures. 3 significant figures. Forget about the 10 times 10 to the power of 15. That's not important when we're looking at significant figures. 1, 2, 3. A 0 to the right of other numbers counts as a significant figure. If it's over to the right hand side here, it counts as a significant figure. 5, 1 and the 0 counts. 1, 2, 3 significant figures. 1, 2, 3 significant figures. That now matches. Question number 5. CCl4 is an effective fire extinguisher and is no longer used because of its toxicity and its role in the depletion of the ozone layer. So depletion means to remove the ozone layer. Ozone is a form of oxygen. Instead of being O2, it's O3. In the upper atmosphere, a bond in the CCl4, well, that's carbon surrounded by 4 Cl atoms, bonded to 4 Cl atoms, so the bond that's broken must be a carbon to chlorine, breaks and the reactive species are formed. A reactive species that's formed in this case is called a radical. Identify the condition that causes a bond in CCl4, we know that's a C to Cl, to break in the upper atmosphere. Deduce an equation for the formation of the reactive species. Well, first of all, in the upper atmosphere, what happens is you get ultraviolet light from the sun, and that's the energy that's needed. The ultraviolet light provides the energy to break the bond. UV light. The equation, well, the CCl4, what actually happens is, in CCl4, one of the bonds between the C and the Cl breaks, and there's a pair of electrons in that bond that's forming a covalent bond. And actually, what happens is, between the C and the Cl, just one of the C to Cls, the pair of electrons separate, and one electron goes onto the Cl as the bond breaks, and the other electron goes onto the C. Now that's come from the mark scheme. I've taken that from the mark scheme, but that dot, that unbonded electron, that's what it is, has come from a bond between the C and the Cl, a covalent bond, a shared pair of electrons, and that's actually gone back onto the C. We know it's gone back onto the C because the C has got 3 Cl's bonded to it, 3 chlorines bonded to it, and it should have 4 bonds. So that electron is on the C to make up for the fact that it's short of a bond. That unbonded electron on the Cl and on this radical as well makes both of these very reactive. One of the reactive species from CCl4 is this one, acts as a catalyst. It means it's going to be reformed in the decomposition, that's the breakdown of ozone. Write the 2 equations to show how the species acts as a catalyst. Well, first of all, we need this, Cl dot, that's the reactive species, and it's going to break down ozone. Now ozone's O3. Now there's only 2 forms of oxygen, O3 and O2, so it must make O2. The Cl dot, the chlorine radical here that's made the reactive species, reacts with O3, ozone, and the only thing it can make, the only other form of oxygen that there is O2. So O3 automatically forms O2. And then you can work out what's left. What haven't we used? Well, we haven't used a Cl, so that must be in there. There's O3, 3 O's makes 2 O's, O2, so there must be an O in there, and then there's a dot, which is an unbonded electron. We've got to show that as well. Now, what actually happens then is that it reacts again. So if it reacts again, then what's actually going to be formed? So well, ClO dot is going to react again, ClO dot, with more ozone. So the depletion of the ozone layer is because the radicals keep reacting with ozone. So ClO dot will react with O3. The only thing it can make is O2, and we can have a look what's left over. So ClO dot that's made the radical reacts again with O3. Now, if it's making O2, look at this. O, O3, there's 4 O's on this side of the equation. 4 O's on this side of the equation, I can balance that up straight away by putting 2 in front of the O2. Now all the oxygens are accounted for and balanced. The only thing that's left then, I've not used a Cl, there it is, and I've not used a dot. And what I've actually done is I've made a catalyst, because the Cl dot rather, at the beginning of this equation has now reacted and reformed. So I've made a chlorine radical here. That unbonded electron makes it reactive, and so it's going to react again and deplete more and more and more ozone, and that's why there's a huge hole in the ozone layer. So any chemicals with Cl's in them, with a Cl in them, especially if the gases and can be released up into the upper atmosphere, are very, very dangerous. because they form radicals. Next question. The next question is hard because of the units, so you've got to know how to convert units. So a small amount of Freon, CF3Cl, with a mass of 1.78 times 10 to the minus 4 kilograms, so kilograms first of all is a problem to us, escaped from a refrigerator into a room of volume 100 meters cubed. Meters cubed is a tricky unit to deal with as well. Assuming the Freon is evenly distributed throughout the room, calculate the number of Freon molecules in a volume of 500 centimeters cubed. So look here, we've got kilograms. We're used to working in grams. We've got meters cubed. We're used to working in decimeter cubed. And we've got centimeter cubed. So we've got a mismatch between some of the units. Give your answer to the appropriate number of significant figures. So we've got to work that out as well. And then we've got Avogadro's constant, 6.02 times 10 to the power of 23. A very large number. That's the number of particles that are in a mole of substance. So we've got a lot of numbers with difficult units to deal with. So how do we start off? What can we start off with? Well, what have we got? We've got a named molecule with a formula, CF3Cl, and we've got a mass. It's in kilograms, but we can convert that to grams if we want to. So we can times that by 1,000 and it'll come out in grams. I've got a mass in grams. I've got an MR. I can work out the MR of this. A carbon has got a mass of 12. A fluorine has got a mass of 19. And Cl has got a mass of 35.5. I've got an MR. I've got a mass in grams. I can work out number of moles of this. Numbers of moles. Moles is a good unit to work with. So let's do that first of all. So the MR of CF3Cl, when you work it out, a 12, 3 19s and a 35.5 is 104.5. I've got the MR of this. Now the mass of this, 1.78 times 10 to the minus 4 kilograms. There's 1,000 grams in a kilogram. So to convert that kilograms into grams, I multiply by 1,000. So that's my next step. I multiply by 1,000, 1.78 times 10 to the minus 4 times 1,000, 10 to the power 3. That's the number of grams. So moles equals the number of grams divided by the MR. Moles is mass divided by MR. So I've put the mass into grams by taking the kilograms and multiplying by 1,000. That's now the mass in grams. Moles is mass in grams divided by the MR that I've worked out, and it comes out as 1.70 times 10 to the minus 3. I've got the moles. Now that's your first step. If you see something with a formula and you've got a mass, it will want you to work out moles. That's always going to be the first step. Now they're a little way in, then we can carry on. So moles of Freon is that. I know that 1 mole of Freon, 1 mole of anything, the number of particles is that. I haven't got 1 mole of Freon, I've got 1.78 times 10 to the minus 3. But the number of moles that I have multiplied by Avogadro's number will tell me how many molecules or particles there are in there. So I've got that number of moles. I haven't got 1. 1 mole would be that amount, that number of molecules or particles. I've got that number of moles. So if I multiply that by by Avogadro's constant, it gives me this number. This number, 1.02 times 10 to the power 21, is the number of particles or molecules that I have in that number of moles, that number of kilograms of Freon. That's the number of particles or molecules that I have of Freon. Now, that escapes into 100 meters cubed. I want to know if I've got that number of particles in 100 meters cubed. If I took a sample of it, 500 centimeters cubed, how many particles would I have? Well, I need to do another little bit of maths, and I'm just going to do this to the side. 100 meters cubed. Well, a meter is 100 centimeters. If I had a cubic meter, a cube that was a meter by a meter by a meter, To do a cube, I take the height multiplied by the length and multiplied by the width. Now a metre is 100 centimetres cubed, so I've got 100 centimetres cubed height cube, 100 centimetres width cube, and 100 centimetres length cube. 100 times 100 by 100 is 1, 2, 3, 4, 5, 6. That's the number of centimetres cubed, a million, 1 times 10 to the power 6, 1 with 6 noughts. That is the number of centimetres cubed in a metre cubed. And it says I've got 100 metre cubed. So that's the number of centimetre cubed in a metre cubed. I've got 100 metre cubed. So that is the number of centimetres cubed, 1 with 8 zeros, 1 times 10 to the power of 8. That's the number of centimetre cubed in 100 metre cubed. I have now got that in centimetre cubed. 100 metre cubed is 1 times 10 to the power of 8, 1 with 8 zeros, centimetre cubed. I only need 500 centimetre cubed, so I'm going to do a fraction. 500 divided by 1 times 10 to the power of 8 is 5 times 10 to the minus 6. That is how much I've got to scale down by. I've got to multiply this number to bring 100 meters cubed down to 500 centimetre cubed, because I know how many particles are in 100 metre cubed. I need to scale down to work out how many particles are only in 500 centimetre cube sample. So that's the number I'm scaling down by. So the number of molecules in 500 centimetre cubed is this number of particles that I had multiplied by my scaling down factor, 5 times 10 to the minus 6, and it comes out as 5.10 times 10 to the power of 15. How do I know about significant figures? What do I do? Well, when I'm looking at numbers here, I've got 1.78 times 10 to the minus 4. I forget about the 10 to the minus 4 when I'm looking at significant figures. I just look at this number here. Forget about the times 10 to the minus 4. 1.78. I've got 3 significant figures there, a 1, a 7 and an 8. 3 significant figures. 3 significant figures. Forget about the 10 times 10 to the power of 15. That's not important when we're looking at significant figures. 1, 2, 3. A 0 to the right of other numbers counts as a significant figure. If it's over to the right hand side here, it counts as a significant figure. 5, 1 and the 0 counts. 1, 2, 3 significant figures. 1, 2, 3 significant figures. That now matches. Question number 6. Dodecane is a hydrocarbon found in the naphtha fraction of crude oil. Dodecane can be used as starting material to produce a wide variety of useful products. The schema in figure 2 shows how one product, polymer Y, can be produced from dodecane. Okay, so what I've got is I've got dodecane making these 2 chemicals here, and then I've got an unknown one here, but this C4H8, lots of these, n number of them, not sure how many, n just represents a number of them are joining together in this polymer. So what actually happens is C4H8 has got the general formula CnH2n, because the 4 doubled makes an N. It's got a double bond in it, and so has this as well. It's got a double bond, and the double bond breaks, and as the double bond between those 2 carbons breaks, it allows an extra bond either side to form, and it forms single bonds, a long chain, a long saturated chain. So I've got C4H8 here, I've got an alkene with a double bond that then breaks to make a chain, a polymer chain of single bonds. Name the homologous series that both C2H4 and C4H8 belong to. Well, general formula CnH2n, that number there, the number of carbons, the 2 gets doubled to a 4 and the 4 gets doubled to an 8. Then the functional group, it's going to be an alkene. It's got double bonds in it, so it's an alkene. Now, what's a functional group isomer? So, a structural isomer is where the molecular formula stays the same, C4H8 stays the same, the molecular formula stays the same, but the structural formula changes. That's a structural formula. So C4H8 has changed its structure. retained its molecular formula but changed its structural formula. So a structural isomer does that, and there's three kinds. Number one, a chain isomer. That's a structural isomer, a chain isomer. Number two is a positional isomer, and number three is a functional group isomer. So a functional group isomer is a structural isomer. It's one of the three kinds. Let's just remind ourselves. A chain isomer might be where I'll take a chain of 4 and make a chain of 3 with a branch. A position isomer is where I might change the position of the functional group. So if that were but2-ene, it might become but1-ene. I change the position of the double bond from a 2 to a 1, change its position in the chain. But it's not, it's a functional group isomer. That means I've got to change the functional group. What identifies it? Well, what identifies an alkene is the double bond. In other words, I've got to retain the molecular formula C4H8, but I've somehow got to get rid of the double bond. So how on earth can I have C4H8 and get rid of the double bond and make single bonds? Well, the only way that I can do that is to make it cyclic. I can put it in a circle. Look, all the carbons have 4 bonds, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, fine, and I've got 8 H's and 4 carbons. I've maintained the structural formula C4H8 by making it cyclic in structure. Identify compound X. Well, I've got to work out what's left over essentially. C12, I've got 12 carbons on that side, I've got 2 there and 4 there. 2 and 4 is 6, and I've got 12 on this side. So I've got 6 missing carbons. That must be C6. That's H26. And I've got 4 and I've got 8. 4 and 8 is 12. So I've got 12 H's on this side. I started off with 26. I've got 14 in there. So it's C6H14. Name the polymer Y. Well, what's happened with polymer Y is this molecule here, before it's made 2 bonds either side, has had a double bond. So this molecule inside the brackets has had a double bond between the 2 carbons, and then lots of these molecules have joined together, the double bond split, and a bond's gone out either side to make a whole long polymer. So it's this chemical here has been this one, but instead of having a bond either side, it's had a double bond in the middle. The longest carbon chain, if you trace it round, it doesn't have to be in a straight line, it just needs to be in some kind of line connected together. 1, 2, 3, 4. So it's had 4 carbons. It's some kind of bute, and it's had a double bond. It's bute with a double bond, butene, and the double bond is between carbons number 1, 2 and 3, 4, 2 and 3. So it's on carbon number 1, 2, but2-ene. And it's a polymer, so we put the word polybutene. So polybutene. So for a name of a polymer, we write down what it's come from, and we put the word poly in front. It's polybutene. That's what it's called. Okay, an example of thermal cracking. So thermal cracking is where you break up a long chain. So I might heat this polymer up and break it up. In other words, reverse the reaction. And when I do so, I tend to make compounds with double bonds in them. So thermal cracking is where I break a long chain up into a series of short chain alkenes. I need a high temperature, and I need high pressure as well. You just got to learn that. Reaction 2 is exothermic. So this reaction here is exothermic. It gives out heat. When I say it's exothermic, it gives out heat when I turn the left-hand reactants into the right-hand products. It gives out heat from left to right. So as it goes left to right, it's exothermic, going to give out heat. When it goes right to left, it's endothermic, it's going to take in heat. Exothermic that way, endothermic that way. Exothermic. A typical compromised temperature of 200 degrees C is used. Okay, explain why the effect of change of temperature on both the position of equilibrium and the rate reaction justify why a compromised temperature is needed. 6 marks. That's hard, that, because we haven't got any of the question broken down. We've got to work out where the 6 marks are. So first of all, I would say the reaction is exothermic, gives out heat. gives out heat in the forward direction. So in other words, when these reactants go to these products, gives out heat in the forward direction. And Le Chatelier's principle then says that what will happen is the equilibrium position will shift to oppose any increase in temperature. So Le Chatelier's principle says that the equilibrium position, that's for a reversible reaction like that, will shift to oppose the change. So what will happen, the effect of a change of temperature? As I increase the temperature, what's going to happen? So I put the temperature up, what's going to happen to this reaction? Well, Le Chatelier's principle says it will shift to oppose any increase in temperature. So let's look back at this reaction here. When it goes from here to here in the forward direction, it gives out heat. If I provide more heat, I make it hot. If it's going that way and making heat, and I provide more heat, what actually happens is it shifts to lower the temperature. If I'm increasing the temperature, its position will shift to try and oppose that change and lower the temperature. Well, left to right, it's making heat. Right to left, it will take in heat. So if I'm providing heat to the system, the way that it can shift and oppose that change, in other words, lower the heat, reduce the heat, make it cooler, is by going right to left, because left to right it makes even more heat. I'm providing heat, it doesn't want to make more, it wants to remove that heat and oppose the change. It will shift right to left. So Le Chatelier's principle says that it's going to shift, the position of equilibrium is going to shift to oppose any increase in temperature, i.e. lower the temperature, and the way it can do that is going right to left. Next one. So a higher level will reduce the yield. So the yield means how much of this is made. Well, if it's going that way and it's exothermic and making heat, and I provide more heat, it will go right to left now to oppose that change and try and lower the temperature. And if it goes right to left, instead of making more of this on the right, it's actually making more of the products that we started with. It's going to lower the yield of the product. A higher temperature provides more molecules have a higher energy. So more molecules have the activation energy or above. That's what happens. The activation energy is the minimum amount of energy for particles to collide successfully. So more particles now have the activation energy and have more successful collisions. And so the rate of reaction will increase. So I've got two conflicting things happening here. I've got Le Chatelier's principle saying that if you increase the temperature, the position of equilibrium will shift to the left and reduce the yield. However, a high temperature is needed because at higher temperature more molecules have the activation energy, so you get more successful collisions and the rate of the reaction increases. And that's why I've got two opposing things happening. At a higher temperature I'm getting a lower yield because the equilibrium position is shifting to the left, but at a higher temperature I'm increasing the rate. So these two are directly in competition with each other. So what actually happens in industry, you use something called a compromise temperature, a temperature that's somewhere in the middle, so that the equilibrium isn't shifted completely to the left and you end up with a low yield, but you have a high enough temperature, you have a high enough temperature so that the rate you've got a reasonable rate, but you've got a not too high a temperature so that the equilibrium shifts too far to the left. Let's look at question number 7, quite a tricky titration question. So what they're doing is this student has decided, he or she, that she's going to put bromine water into a burette. She's got bromine water into a burette. She's using a drop-in pipette to add 5 drops of oil, and the oil has got carbon-to-carbon double bonds in it, into a flask. It's worrying me that she's using a drop-in pipette and 5 drops of oil. You wouldn't use a drop-in pipette. You'd use a normal pipette. You wouldn't use such a small volume of 5 drops of oil. So that's immediately making me think that there's something wrong with this experiment. But anyway, we've got bromine water in the burette. We've got a very small amount of oil using a drop-in pipette into a flask. The oil has got carbon-to-carbon double bonds in there, and we're pouring the bromine water from the burette into the cooking oil that's got carbon-to-carbon bonds. The bromine water is orange, and when it reacts with carbon-to-carbon double bonds it goes colourless. So the orange colour from the burette will go into the cooking oil and turn colourless. At the point that all the cooking oil is used up, then the bromine water that's orange will come through into the cooking oil. There'll be no more cooking oil with any more double bonds in there to react, and so the orange colour will start to colour the flask because there's no cooking oil to take the colour out of it, to decolorise it and to turn it colourless. So we're looking for a colour change of orange into the flask as the bromine water comes through and is unable to react anymore. Okay, I've got some volumes here of the bromine water. Let's have a look at the first bit of the question. In the trial experiment, the student failed to fill the burette correctly, so that there's a gap. Suggest the effect. Okay, so you've got the burette here, and you've got an air gap in the bottom of the burette. Well, let's say that the air gap is 3 centimeters cubed. The first 3 centimeter cube that's pouring out of the burette is actually not going to pour out of the burette at all. It's going to fill the air gap. So if we think we've delivered, let's say, 10 centimeters cubed of bromine water from the burette, because the volume's gone down by 10, we've actually not. We've only delivered 7 out of the burette, because the first 3 centimeters cubed went to fill the air gap. So we've only delivered 7, but it seems on the burette as if we'd delivered 10. So, suggest what it would have on the measurement. The measurement is 10, but we've only delivered 7. The measurement is higher than we'd expect. So the measured volume is greater than we'd expect, higher than we'd expect. And the reason is because the bromine water has to fill the gap before any of it's delivered. Other than the incorrect use of the burette, suggest a reason for the inconsistency in the student's results. I really don't like using a drop-in pipette here. A drop-in pipette is not an accurate measure of anything. It doesn't measure volume accurately because the drops that come out of a drop-in pipette are all kinds of different sizes. The drop sizes vary from a drop-in pipette, not a good measure of volume at all. Drop sizes vary from a drop-in pipette. Outline how the student could improve the practical procedures to determine the number of carbon-to-carbon double bonds in a molecule of oil so that more consistent results are obtained. Okay, as well as using a drop-in pipette, well, I wouldn't use a drop-in pipette at all, you've got a problem. Because in this flask, you've got 5 drops of an oil and 5 centimeters cubed of an organic solvent. 5 centimeters cubed and 5 drops is a very, very, very small amount. It's going to be very difficult to measure or see the change in colour in that very small amount. And it's too small amount to use. In a flask, when you're doing a titration, you need 25 centimeters cubed. That's the standard amount that we use in a flask so that you can see and measure the reaction change accurately. So first of all, I'd use a larger volume of oil. 5 drops is not enough. Secondly, I'd mix it with the organic solvent. Next, I'd transfer into a larger flask to make up a batch of it, maybe 250 centimeters cubed with more of the solvent. So you've got a batch of the solvent. You always make a batch of chemicals that you're going to use, and then you take 25 centimeter cube samples for the flask. So more oil, 5 drops is not enough. Dissolve it in the organic solvent, make a batch up so it's all the same concentration, and you've made it up at the start and you've got a concentration of that at the right concentration up to 250 centimeters cubed is a good amount to make as a batch, and titrate 25 centimeter cube samples in the flask. That's a more acceptable volume to be titrating against. Let's have a look at this one now, this question here. It's for 5 marks and it's unscaffolded. In other words, it's not led you through, it's not said what steps to take. However, we have some big clues in here. An oil has a density. That word density, there's only one thing you can do with density. Density is mass divided by volume. That's the only equation you've got for density. Density, mass divided by volume. We know we're using that equation, so we've not even got to look any further down. We know density is mass divided by volume. We're going to be using that. Let's do that first. 5 drops of an oil has a volume. Right, so it's given me volume, 5.0 times 10 to the minus 2. Density is mass divided by volume. 0.92 is mass divided by 5.0 times 10 to the minus 2. Density is mass divided by volume, so mass is density multiplied by volume. You're multiplying those two numbers, first of all, to get the mass of the oil. The mass of the oil, 0.92 times 5 times 10 to the minus 2. Now you've got to put a 5 in there as well. Each of the drops has a volume of those, and you're using 5 drops. So that's potentially where you'd make a mistake, because each drop of oil has a volume of 5 and you've got 5 drops. So the total mass of oil you need to times by 5 because you've got 5 drops, 0.23 grams. What's next? Right, I've got the mass of the oil, I've got an MR. So now I need to convert it into moles. The only equation with MR in it is moles is mass divided by MR. So 0.23 divided by 885 will give me the number of moles of oil. Moles is mass, 0.23 divided by the MR, 885, 2.6 times 10 to the minus 4. That's the number of moles of oil that I have. What have I got next? I've got the concentration of bromine water. Again, this is leading me in. Concentration is moles divided by volume. Concentration is moles divided by volume. So I'm going to need the volume to be able to work out moles. Where can I get the volume of bromine water? Well, it says I'm using experiment 1. And back here in experiment 1, the volume of bromine water is 39.4. So if I look back in the experiment, I've got 39.4 centimeters cubed of bromine water. I've got the volume of bromine water that I've used. So concentration is moles divided by volume. Concentration moles divided by volume. Moles is concentration multiplied by volume. So I take the concentration, 2.0 times 10 to the minus 2, and then multiply by the volume, which is 39.4, and I'll come out with the number of moles. However, this in centimeter cubed needs to be in decimeter cubed, so I need to divide by 1,000. So 39.4 centimeter cubed is 0.0394 divided by 1,000. That's the volume I use, 0.0394. So concentration is moles divided by volume, 0.0394 times 2 times 10 to the minus 2 will give me 7.9 times 10 to the minus 4. I now know the moles of bromine water. So by looking at the information I've given, it's led me through the question, and I've got 3 marks already out of the 5. Use this data to determine the number of carbon-to-carbon double bonds. Well, 1 mole of oil reacts with, or should do, 1 mole of oil should react with 1 mole of bromine water, but only if there's 1 double bond in there. So it's actually the bromine water has reacted with the double bond. So if the oil has got 1 double bond in there, then 1 mole of oil, because it's the double bonds that are reacting, 1 mole of oil with 1 double bond in there would react with 1 mole of bromine water. However, they're not the same. That's not 1 and 1. If that were the same amount as each other in a 1-to-1 ratio, there'd be 1 carbon-to-carbon double bond. But it looks like I'm needing a lot more bromine water, 7.9 times 10 to the minus 4, compared to 2.6 times 10 to the minus 4. That means there's not 1 mole of carbon-to-carbon double bonds in there. If I look at this ratio, 2.6 times 10 to the minus 4 to 7.9 times 10 to the minus 4, if it were a 1-to-1 ratio, there'd be 1 double bond in the oil, but there must be more than 1 double bond in the oil because I'm needing a lot more bromine water, a lot greater number of moles to react with the oil. So what I do is I look at the ratio. The amount of oil that I have, 2.6 times 10 to the minus 4, compared to bromine water, 7.9 times 10 to the minus 4. The reason I need, it looks like I need 3 times the amount of bromine that I do for oil. 3 times. This times 3 comes out as 7.9 times 10 to the minus 4. 2.6 times 10 to the minus 4 times 3 comes out roughly about 7.9. So the ratio is 1 mole of oil to 3 moles of bromine water. That means I need 3 moles of bromine water to react with 1 mole of oil because there's 3 double bonds in the oil. That's why I need 1, 2, 3 moles of bromine water to react with the 1, 2, 3 double bonds in every molecule of oil. Let's look at questions 8 and 9. So which of these samples of gas contains the largest number of molecules? Well, first of all, another way of looking at that is you get the number of moles and then you multiply by Avogadro's number to get the number of molecules. So another way of saying this is which of these has got the largest number of moles, because you're going to multiply each of them by the same number, Avogadro's number, to get the number of molecules. So you can miss out that step and just reinterpret this question as saying which of these has got the largest number of moles. So how we're going to do that? Well, PV equals nRT. You've got to use PV equals nRT. I would think that's fairly obvious because you've got R, the gas constant, in there, and PV equals nRT is the only equation you know with the gas constant in there. N is the number of moles, so you've got to rearrange it. Let's have a look at spoilers. So PV equals nRT, divide both sides by R and divide both sides by T to cancel the R and the T on that side. So N equals PV divided by RT. So I've got to work out PV and divide by R and T. Well, let's have a look at these. Pressure is in pascals, so sometimes it's in kilopascals and you need to multiply by 1000 to turn into pascals, but none of these are in kilopascals, so that's fine. So pascals, the pressure here is fine. Temperature in Kelvin, so sometimes you've got to convert degrees Celsius into Kelvin by adding on 273. So 273 add degrees C turns it into Kelvin, but they're all in Kelvin. So our pressures and our temperatures are all fine in the same units. However, look at some of these. A and B, the volume is in meter cubed, and that's correct. Whereas these ones, C and D, it's in decimeter cubed. So I need to get everything into meter cubed. So the volume has got to be a meter cubed. So how do I turn decimeter cubed into meter cubed? Well, the answer is that I've got to divide by 1000. So to turn decimeter cubed into meter cubed, you divide by 1000. If you want to know how that works, well, think about what a meter cubed is. A cube has got a length, a height, and a depth to it, a width. So you multiply those 3 values together to get the volume of a cube. So length, height, and depth or width. And a meter is 100 centimeters. So 100 multiplied by 100 multiplied by 100 is 1 times 10 to the power of 6. 1 with 6 zeros after it. A decimeter cubed is 1000 centimeter cubed. So a meter cubed is 1 times 10 to the power of 6. A decimeter cubed is 1 times 10 to the power of 3. Or in other words, you could say a meter cubed is 1,000,000, 1 with 6 zeros, centimeter cubed, and a decimeter cubed is 1000 centimeter cubed. So a decimeter cubed is 1000 times smaller than a meter cubed. So you've got to take this value and divide by 1000 to turn decimeter cubed into meters cubed. And then if you put the numbers in, N is this value, so N is P times V, so 5 times 10 to the power of -4. 5 times 10 to the -4 is your volume, multiplied by your pressure, which is 1 times 10 to the power of 6 there. So 1 times 10 to the power of 6 is your pressure. This is your volume, 0.0005, 5 times 10 to the -4, divide by R, divide by T, and it comes out as 0.2. You do the same for all of them. Remember, you've got to take this 3 times 10 to the power of 1 and divide by 1,000. So 3 times 10 to the power of 1 is 30 divided by 1,000. So you've got to divide these two by 1,000 here. That's why those two have got divided by 1,000 to turn decimeter cubed into meter cubed, and therefore you come up with the answers, and 0.24 is your highest number of moles. You could multiply each of these by Avogadro's number, but you'd still find that B is the highest value. Which of these substances, question 9, which of these substances has permanent dipole-dipole attractions between the molecules? CCl4, C2F4, CH3 twice CO, so that's propanone and carbon dioxide. Well, let's have a look at the molecules first of all. So CCl4 is carbon surrounded by 4 Cls. C2F4 is double bonded carbons surrounded by 4 Fs. Propanone is CH3 with a C double bond O in the middle. It's a ketone, propanone, and carbon dioxide is CO2. If you've got permanent dipole-dipole attractions, it means that any polar bonds, that is, any bonds with delta plus and delta minuses, will not cancel each other out. So say for example CCl4, there's a polar bond there between the C and the Cl. Cl is electronegative, can have a small minus charge, the C will have a slight plus charge, but because it's completely symmetrical in both the Y and the X axis, all of the polar bonds, the delta plus and delta minuses, cancel each other out, and therefore you don't get permanent dipole-dipole attractions between the molecules, because the overall charge here in all directions cancels each other out. So another way of looking at this is, which of these has permanent dipole-dipole attractions between molecules? In other words, is not completely symmetrical. If it's completely symmetrical, you won't get permanent dipole-dipole attractions between molecules. So CCl4 is permanent, has no permanent dipole-dipole attractions because it's completely symmetrical in both the y-axis and the x-axis. If we look at C2F4, that is, then it's symmetrical about the y-axis and it's symmetrical about the x-axis. Propanone, C, I think is your answer here, because if you look at it, it's got symmetry, it's symmetrical about the y-axis, but it's not symmetrical about the x-axis. If you look on the x-axis here, you've got a C double bond O coming up, but you've not got a C double bond O going down. So that's going to have permanent dipole-dipole attractions because that molecule is not perfectly symmetrical in both directions. Carbon dioxide, let's just check this out. It has a line of symmetry, is symmetrical about the y-axis and the x-axis, so that won't have permanent dipole-dipole attractions between molecules. Your answer is C. Let's have a look at questions 10, 11 and 12 now. What is the total volume of gas remaining after 20 centimetres cubed of ethane, so that's your ethane there, burned completely in 100 centimetres cubed of oxygen? All volumes are measured at the same pressure and same temperature, which is above 100 degrees C. So the 100 degrees C tells you that the water will have boiled, so that'll be steam, so that'll be water vapour or steam, so that's a gas as well. In other words, everything, the ethane, the oxygen, the carbon dioxide and the steam are all gases. So what actually happens is, with a gas at a certain temperature, it doesn't matter which gas it is, they've got all the same volume. So say for example at 25 degrees C or 298 Kelvin, all gases have a volume of 24 decimeter cubed. So what you can do is, if I say 1 mole of that reacts with 3.5 moles of that to make 2 moles of that and 3 moles of that, then we can say that the volume ratio is the same as the mole ratio. So 1 say for example decimeter cubed of that would react with 3.5 decimeter cubed of that to make 2 decimeter cubed of that and 3 decimeter cubed of that. So let's have a look then. If say for example 20 centimeter cubed of ethane, so 20 of that, 20 centimeter cubed of ethane would react with 3.5 multiplied by 20, so 3.5 20s is 70, would react with 70 centimeter cubed of that. 20 centimeter cubed of this, 1 reacts with 2, so would react with 40 of that, and would make 1 to 3, would make 60 centimeter cubed of this. So let's have a look again. So 1 mole of that reacts with 3.5 moles of that to make 2 moles of that and 3 moles of that. All volume ratios are equal for gases at the same temperature and pressure. So in other words, 1 centimeter cubed of that would react with 3.5 centimeter cubed of that to make 2 centimeter cubed of that and 3 centimeter cubed of this. So I've got 20 of that, I react with 70 centimeter cubed of this to make 40 centimeter cubed of that and 60 centimeter cubed of this. Let's have a look at spoilers then. So 1 centimeter cubed of ethane reacts with 3.5 centimeter cubed of oxygen to make 2 centimeter cubed of carbon dioxide and 3 centimeter cubed of water. So I've multiplied up by 20. So 20 centimeter cubed of this react with 70 centimeter cubed of that to make 40 centimeter cubed of that and 60 centimeter cubed of water. So your 20 centimeter cubed of this is gone. 70 centimeter cubed of this has gone. I've got 100 centimeter cubed to start with. So if 70 centimeter cubed of the oxygen is gone, then I've got 30 centimeter cubed left over. I've made 40 centimeter cubed of this and 60 centimeter cubed of this. 40 and 60 is 100. Add the 30 centimeter cubed of oxygen that's left over. 130 centimeter cubed. Your answer is D. Consider the reaction between propene and hydrogen bromide to form a major product. Well, let's actually have a look at the mechanism of the reaction. So here we've got propene. Let's just check. 1, 2, 3 carbons. Yes, prop. We've got an ene, a double bond in there as well. So the double bond will react and attack the H of the Br because that's slightly delta plus, this is slightly delta minus. So the electrons, the electron-rich double bond will attack the delta plus of the H, and the electrons in the HBr covalent bond will move on to the Br. That then will make the double bond break, and it will make Br minus with a lone pair of electrons and a minus charge. The question is, where's the H going to go? Where does this H go? So if you actually want to know where it goes and not so bothered about why it goes there, if you look at the 2 carbons here, it goes onto the carbon with the most number of hydrogens. So this carbon has got 1 H, this carbon has got 2 H's, so it goes onto the carbon already with the most number of H's, so it's going to go onto this one. So it goes here and leaves this carbon without enough bonds, 3 bonds. If it's not got enough bonds, it's lost an electron from a bond and it becomes plus. We call this a carbonium ion, a C with a plus. And that's stable because it's in between, in the middle of a chain. The exact reason is that these 2 methyl groups either side, the 2 CH3s, repel electrons and reduce the size of the plus charge, making it stable. So this C with the plus, a carbonium ion, has got 2 other carbons attached to it, bonded to it. So it's a secondary carbocation, or a carbonium ion, secondary carbonium ion, or a secondary carbocation. And this then will get the Br attacked to it. So the answer is going to be, this is your intermediate here, this is this, CH3C with a plus HCH3, and in actual fact if you took it further you'd make 2-bromopropane from it in the end. The answer is this one here. This is your intermediate, the thing that's formed, the species that's formed part way through the reaction, in the middle of the reaction, before the final product's made. The answer is C. Which of these substances reacts most rapidly to produce a silver halide precipitate with acidified silver nitrate? So I've got CH3Br, CH3Cl, CH3F and CH3I. So you need to know which is the strongest bond. So the carbon to Br, the carbon to the Cl, the carbon to the F, or the carbon to the I. So if you look at it, CF is the strongest bond, CCl is the next strongest bond, CBr is the next strongest bond, and Ci is the weakest bond. The reason that is because F is the smallest of these atoms. It's at the top of group 7, smallest atom. Next smallest atom is the Cl, Br is the next smallest atom, and I is the largest atom. So in terms of the strength of the bond, when you're talking about the atoms getting closest together and holding on to the covalent bond in between the two atoms, the Ci, because the I is so large, the C to I bond is longer than the other three, and so therefore this is the weakest bond. If this is the weakest bond, it's going to break most rapidly, and the silver iodide that's formed as a yellow precipitate will be formed most quickly. So your answer is D. Let's look at questions 13 through to 15 then. Which statement about E12-dichloroethene is correct? So let's have a look at what E12-dichloroethene is. So ethene 2 carbons, joined with a double bond, the ene, and I've got a Cl, 2 Cls dichloro, 1 Cl at number 1, carbon number 1, and 1 Cl at carbon number 2, so they're on opposite carbons. Because there's a double bond, there's no fixed rotation about the double bond, and if you look to the left of the double bond, you've got H and a Cl, and to the right of the double bond, you've got an H and a Cl. So to the left of the double bond, you've got two different groups, an H and a Cl, and to the right of the double bond, you've got two different groups, a H and a Cl as well. So it's going to have geometrical isomerism, which is a form of stereoisomerism, and it will have E isomers, where the Cl, the atom that takes highest priority because it's got the highest atomic mass, can be at the top or at the bottom. If one Cl is at the top of the carbon-to-carbon double bond and one is opposite on the bottom, it's an E isomer. If they were both on the top or both on the bottom on the same side of the carbon-to-carbon double bond, it would be a Z isomer. So it has the same boiling point as Z. E and Z, do they have the same boiling points? Do the positions of the Cl being either up or down affect the boiling point? Well, yes, they do, because a C to Cl double bond is polar. It's got a delta plus and a delta minuses, and if both of those polar bonds are on one side of the double bond, it will affect the dipole-dipole attractions, the intermolecular forces between the molecules, and it will affect the boiling points. So E and Z will not have the same boiling points. It forms a polymer with the same repeating unit as Z. Well, in actual fact, I think that one's true, because the carbon-to-carbon double bond breaks and forms single bonds. So once they've formed single bonds, there is no fixed, the atoms are not fixed in positions in space, because a single bond does have free rotation. So the Cl's are free to move up and down because the carbon-to-carbon single bonds can rotate. So it's no longer fixing the positions of the Cl groups in space, and therefore the repeating unit will be the same irrespective of whether it's come from an E or a Z isomer. It has the same infrared spectrum as Z12-dichloroethane in the range 400 to 1500 centimeters cubed. Well, we haven't got anything in that range anyway. A carbon-to-carbon double bond is 1620 to 1680, so that range is wrong for a start. It has a molecular ion peak different from that of Z. Well, what happens is in molecular ions is that these molecules lose an electron, and when they lose an electron, then they get a positive charge, and the positive charge then is called a molecular ion, and you can measure the relative formula mass of that ion. Well, it won't actually affect E or Z are going to have the same MR. So when you form a molecular ion, it's the positions of these Cl's which are different between E and Z. They've got the same relative formula mass, they've got the same MR, and therefore the molecular ion won't be different between these two. So D is wrong. So your answer there is B. Which statement about ethene is correct? It has no geometrical isomers because there's no free rotation around the carbon-to-carbon double bond. Well, that's true in that there is no free rotation about the carbon-to-carbon double bond, but it's not the reason that this has no geometrical isomers. The reason it doesn't have any geometrical isomers is ethene, so it's carbon-to-carbon double bond with two H's to the left of the double bond and two H's to the right of the double bond. If you look to the left of the double bond, you've not got two different groups, you've got two H's, and to the right of the double bond, you've not got two different groups, you've got two H's. So the reason it doesn't have geometric isomers is because there are two groups which are the same to the left of the double bond, and also two groups to the right of the double bond which are the same. So that's the reason it doesn't have geometrical isomers. It reacts with HBr in a nucleophilic addition reaction. No, it reacts with HBr in an electrophilic addition reaction. So nucleophilic is wrong. So nucleophiles such as OH minus or Br minus would react with something with a slight delta plus. So a double bond which is high in electrons is electrophilic addition. It burns in excess oxygen to produce carbon dioxide and water. Yes, any hydrocarbon will burn in oxygen, excess oxygen that is, to produce carbon dioxide and water. The word excess is important, so if there's not a plentiful supply of oxygen, then it would be incomplete combustion rather than complete combustion. There'd be incomplete combustion, and it may form something like carbon monoxide or even carbon as a black solid. But in excess oxygen, it will produce carbon dioxide and water. So C is correct. The C double bond is twice as strong as the carbon-to-carbon double bond in ethane. Well, you can't make that assumption. In actual fact, that's not true. The carbon-to-carbon double bond isn't twice the strength of a carbon-to-carbon single bond. Which statement about ethanal is correct? So ethanal is an aldehyde, CH3CHO. It reacts with toluenes to form silver. Well, that's true straight away. An aldehyde does react with toluenes reagent to form a silver mirror. It would also react with Fehling solution to form a brick red precipitate. It has a higher boiling point than ethanol. Now, ethanol has an OH group, so an oxygen bonded to a hydrogen. Anytime that you get hydrogen bonded to an oxygen, or a fluorine or a nitrogen atom, then that is a very polar bond with large delta plus and delta minuses, and therefore the dipole-dipole attractions between molecules is very strong. That's something called hydrogen bonding. So when you get H bonded to an O, an F, or a B, or an N, then you get hydrogen bonding, which is the strongest form of intermolecular bonding, and that's what ethanol will have. So that'll have a high boiling point, higher than ethanal, which has just got polar bonds and dipole-dipole attractions between the C double bond O, which is a polar bond, and other C double bond O's of sort of nearby molecules. Its empirical formulas and molecular formulas are different. No, they're not. They're the same. You've got CH3CHO, so the molecular formula will be C2H4O. Since it's got one oxygen in it, you can't simplify that to form a simpler empirical formula. It belongs to the homologous series with the formula CnH2nO. No, we've just said it's C2H4O, so it will be CnH2nO. So A is obviously a correct answer. Questions 16, 17 and 18. Which of these substances does not contribute to the greenhouse effect? So the greenhouse effect is where infrared light from the sun is expected to reflect off the Earth's surface and go back out into space. However, sometimes the gases absorb the infrared light and prevent it then from reflecting back out into outer space. They warm up and contribute towards the greenhouse effect. Which gases will do this? Unburned hydrocarbons such as methane. Yes, they will contribute to the greenhouse effect, so the bonds within them will absorb infrared light. Carbon dioxide will do too. So carbon dioxide produced during the complete combustion of hydrocarbons in a plentiful supply of oxygen. Water vapour will do too, so that's a common mistake to think that water vapour doesn't contribute towards the greenhouse effect, but the hydrogen to oxygen bonds in water vapour actually absorb infrared light as well. Nitrogen, 79% of the Earth's atmosphere is nitrogen. It's an inert gas, an unreactive gas that won't absorb infrared light. The answer is D, nitrogen. This is a tricky kind of question because they've done a mechanism here in a way that I wouldn't normally do it. So the way that I would react this is that you've got ammonia with a lone pair of electrons acting as a nucleophile, a lone pair donor attacking the C center. That's perfectly acceptable with a delta plus on the C, because the CBr is a polar bond. The Br is electronegative and draws electrons towards itself, so this will have a delta plus charge on it, and the Br would have a delta minus charge on it. Perfectly acceptable at NH3. A nucleophile will attack a delta plus center, and perfectly acceptable then that the Br will accept the electrons from the double bond, from the single bond rather, the electrons from the bond onto itself and form Br minus with a lone pair of electrons. Perfectly acceptable, both of those arrows. What I would then normally do is I would have the Br coming off, being substituted, and the NH3 bonding to the C, and there'd be a plus on the N, and one of the H's then would break off with the electrons from the bond going onto the N plus and forming an NH2 group on here. That's the way that I would do that mechanism, that nucleophilic substitution mechanism. They've done it slightly differently here. They've got another ammonia with a lone pair of electrons accepting an H plus. That will form NH4 plus an ammonium ion. Then the problem, and that's perfectly acceptable, the problem then is that this electron pair from here should actually, from the NH bond, actually go onto the N plus and cancel out the N plus. So that should be the way that would work. Arrow number 4 is incorrect. A tricky question there, because you've got a mechanism that's overly complicated. Which statement about the reaction is not correct? Ethylamine is a primary amine, so you've got CH3, CH2, and it's going to form NH2 on here. The N, H2, the N is bonded to one carbon. The N bonded to one carbon is a primary amine. The mechanism is nucleophilic substitution. Yes, it is. So this NH3 is going to attack the C plus and substitute for the Br. And this is a nucleophile, an electron pair donor, perfectly acceptable. Using an excess of bromoethane will stop further reaction to form a mixture of amine products. Now it actually won't, because when you form CH3, CH2, NH2, ethylamine, the N of the ethylamine will have a lone pair of electrons, and so it will react again to form diethylamine, and then react again to form triethylamine, and then react again to form a quaternary ammonium salt. So the fact that you've got excess bromoethane will mean that the ends of the ethylamine, the diethylamine and the triethylamine will actually carry on reacting. So C is incorrect. Ammonium bromide, that's NH4 Br minus. Bromide is a Br minus ion, and ammonium is an NH4 plus ion, is an ionic compound. Yes, it's going to form an ionic solid, so D is correct. So C is the incorrect answer. Let's look at questions 21 and 22. So what are you doing here? You're mixing some sodium thiosulfate with some hydrochloric acid. You're looking down through this mixture towards a paper mark with a cross. So what actually happens is that this mixture then becomes cloudy, and so you can measure when the reaction's complete or reached a certain stage when you can no longer see the cross. So what's likely to decrease the accuracy of the experiment? What's going to be a poor idea? If you rinse the flask with acid before each experiment, then some acid is going to be lining the flask, and therefore you're going to get the incorrect volume of acid. You're going to get too much acid in the flask, and each time you rinse it you might get a different amount of acid then lining the flask. That's going to cause some extra acid to be in the flask, and it might be a different amount each time. A is really a poor idea, so that looks to be the answer. Decrease the accuracy of the experiment. Let's check the rest. Stir in the solution, always a good idea throughout each experiment to ensure that there's consistent mixing each time. Use the same piece of paper for each experiment, a good idea, because sometimes if you use a thicker cross one time than the next, then it's going to be more easily viewed down through the cloudy mixture. Using different measuring cylinders to measure the volumes of acid and sodium thiosulfate, a good idea there, because you're not going to get contamination between the two if you're using slightly different measuring cylinders. So your answer, the poor idea, is A. The experiment was repeated at 20 degrees C using a larger 250 centimetre flask rather than a 100 centimetre flask. So what effect's that going to have? Well, you've got the same amounts, the same number of moles of chemicals, except that you've got a larger flask. If you've got a larger flask, then the particles are further apart. So the collisions, you can get fewer successful collisions in a set amount of time. So the fact that the particles are further apart with fewer successful collisions in a certain amount of time means that the rate is going to decrease. It's going to go slower. So the timetable will be not affected by using a large conical flask. No, the rate is going to go slower. Remember, if a rate goes slower, then the timer is going to take more time to complete the reaction if the reaction is going slower. So the time taken will be increased rather than decreased, so that's incorrect. The time taken will be increased by using the large conical flask. C is correct, so the reaction is going slower, the time taken is increased. It's impossible to predict how the time taken will be affected. Now we've worked out the reaction is going to go slower and the time is going to increase. Your answer is C.